My name is Alexandra and I'm a PhD candidate at the chair of Heiko Mantel at TU Darmstadt. Together with my colleague Weinert from Encrypto at TU Darmstadt, I'm presenting the article RiCaSi, Rigorous Cache Side Channel Mitigation via Selective Circuit Compilation, which is joint work with Heiko Mantel, Lukas Scheidel, Thomas Schneider, Weinert and Tim Weißmantel. I will start with the motivation for cache side channel mitigation via circuit compilation. In an ideal world, cryptography can be implemented at a high level of abstraction. For example, using lookup tables for the implementation of block ciphers. Such implementations are close to the specification of the crypto algorithm and are hence easy to develop and to maintain. They can also achieve a high performance. For example, lookup tables were introduced into the AES specification as a way to increase performance of the implementation. Maybe you can imagine this like riding a horse on a road in ideal conditions. There are known interfaces and tools for communicating with the horse, like for example the saddle. But now in reality, things are not so easy. In lookup table-based crypto implementations, secret-dependent memory accesses might cause secret-dependent contents that gets loaded into the cache. And an attacker who shares the cache, for example because he's co-located on a cloud machine, might be able to deduce secret information like crypto keys from this cache. So, lookup table-based implementations are prone to cache side channels, and there's in fact a danger of full key recovery, as was shown for example by Oswik, Shamir and Shroma already in 2006. So maybe you can imagine this like now riding your horse under less ideal conditions, for example wanting to cross the ocean with the horse. Luckily, you don't need to use the horse to cross the ocean. There exist solutions how to deal with these real conditions. In particular, there's a way to implement crypto in a way that simulates a circuit with logic gates and software. And by computing all results on the fly using these gates, this solution avoids memory accesses completely and therefore also avoids secret-dependent memory accesses. Unfortunately, circuit-based crypto implementations are at a very low level of abstraction, so they are very far away from the original crypto specification. Maybe you can imagine this like riding a dolphin to cross the ocean. The dolphin is very elegant and is very well suited for crossing the ocean, but the interface is very different and very much low level compared to the interface of a horse, so there are no saddles for dolphins. It's really a more complicated thing to do. And our goal is to combine the simplicity of high-level crypto implementations with the security you can get by circuit-based crypto implementations. So we want to support developers so that they can work on the high level of abstraction, maybe implement their crypto based on lookup tables, and still obtain a circuit-based executable. To this end, we want to leverage existing infrastructure that was originally intended for other purposes, but that we will make fit for the use in sidechannel mitigation. So speaking in the metaphor, we would like to equip the horse with a surfboard so that it can be adjusted to the real-world conditions, but the interface remains the same that you have known from the high level. And the key idea in our article is to use a combination of circuit compilation and program analysis. Circuit compilers are an existing concept from the area of secure computation. They compile high-level implementations to a circuit format. Originally, they are intended for oblivious function evaluation in protocols, but our idea is to repurpose these circuit compilers to also use them in sidechannel mitigation. In this new environment, two key challenges arise for the use of circuit compilers. First, circuit compilation is quite expensive. It requires manual preprocessing to map the program you want to compile into the sublanguage that is supported by the circuit compiler, and it also introduces runtime overhead. Second, circuit-based implementations need to be run on real systems. While an abstract circuit avoids any side channels by design, for actually running the circuit it needs to be refined to a concrete executable. And this refinement step might introduce new vulnerabilities. Actually, I know anyone could say this now, but this is something that actually happened to us. In our first try to use circuit compilation for side channel mitigation, we actually accidentally introduced such vulnerabilities. And therefore our goal is to provide an approach that avoids, if possible, the overhead, and that definitely avoids the introduction of new vulnerabilities, so that we can actually rely on the circuit-based executable. To this end, we use program analysis to complement the circuit compilation. In the first stage, we apply program analysis to guide the mitigation, so that circuit compilation is only applied when necessary. In addition, we apply program analysis after the circuit compilation to ensure that the final executables that we get after circuit compilation are secure. The contributions of our article are first this approach to cache side channel mitigation, which allows a crypto developer to work on the high level of abstraction that he is used to, but still yields executables that are secure with respect to a threshold for cache side channel leakage. We achieve this by a combination of circuit compilation for hardening the implementations, program analysis for avoiding unnecessary overhead, and program analysis to ensure the reliability of the hardening. We implement this approach in the toolchain RiCaSi, which takes a high-level crypto implementation in C and then produces an x86 executable that comes with a security guarantee against cache side channel leakage. We successfully applied RiCaSi to multiple crypto implementations from libraries like OpenSSL and TLS, which are lookup table based and therefore initially vulnerable to cache side channels. And in the end, with RiCaSi, we obtain hardened x86 executables that achieve zero leakage guarantees against cache side channels. And finally, we also evaluated the overhead introduced in terms of running time and size of the executables. As I mentioned in the introduction, circuit compilation does of course introduce overhead, but we think that the results are practical, and also here we see the key advantage that RiCaSi only selectively introduces this overhead and does not apply the circuit compilation to every binary. Before we go into the details of the evaluation in terms of both security and overhead, I will start with a walkthrough of the RiCaSi toolchain. In the first phase, RiCaSi ensures that circuit compilation is used only when necessary. To this end, we take high-level C code and compile it to an x86 binary. We then apply an automatic side channel analysis next, and this analysis provides a security guarantee in the form of an upper bound on the cache side channel leakage of the binary. If this bound is already below the threshold of acceptable leakage, we are done, and the binary can be used directly without any overhead. If the security is not strong enough, that is, if the leakage bounds are higher than the desired threshold, then we move into the second phase of RiCaSi. In this case, the next step is pre-processing of the C code for circuit compilation. This step happens manually, but only involves a simple high-level rewriting to map the code, the C code, into the subset of C that is supported by the circuit compiler. To this pre-processed code, we then apply the automatic circuit compiler, which outputs an abstract circuit description. The circuit description we then transform into C code, that is then again compiled to a new x86 binary. To ensure that no leakage was introduced in the refinement from this abstract circuit to the concrete x86 binary, we apply a second round of program analysis, and this analysis gives us an improved security guarantee. If this guarantee is then below the desired threshold, the new binary can be used. In our evaluation, even given that we started with a vulnerable implementation, we always achieved a zero leakage bound at this stage, so the resulting executables are secure with respect to the lowest possible leakage threshold, which is great. So with RiCaSi, we now have an implementation of our approach for circuit compilation guided and secured by program analysis to achieve executables that are secure with respect to cache side channels in a rigorous way with security guarantees, but also in a selective way that only applies the mitigation where necessary. I will now walk you through the RiCaSi toolchain at a concrete example. To this end, let's look at the example of the AES implementation from OpenSSL in the lookup table-based version. Let's set the acceptable leakage threshold for this example to 0-bit. As you can see here, the original lookup table-based implementation looks like this. So we have the variable S0, which contains part of the secret key, and then we access one of the lookup tables at a location that depends on this S0. So we have here secret dependent memory access. To analyze the leakage of this original implementation, we apply the side channel analysis step in RiCaSi. In this step, we perform a quantitative program analysis on the x86 binary corresponding to the high-level C code that we have just seen. This analysis computes reliable upper bounds on the cache side channel leakage with respect to multiple attacker models. On the one hand, we have two attacker models that model access-based synchronous attacks like prime and probe or evict and time. And on the other hand, we have models that model trace-based attacks and attacks based on the timing difference introduced by the interaction with the cache. This program analysis augments the analysis from the tool cache audit in 2 dimensions needed to handle circuit binaries. First, we augmented the parsing so that it scales to the large control flow graphs of circuit-based binaries. And second, we augmented the formal model of execution in the analysis by support for additional x86 opcodes needed for circuit binaries. How does this formal model of execution work? In the theory underlying the analysis, we first model the leakage to cache side channels using information theory. This leakage is then upper bounded by the logarithm of the observations that an attacker could possibly make, and we over-approximate these reachable observations using program analysis based on this formal model of execution, which is an abstract semantics that over-approximates the possible executions of the x86 binary. That is, the leakage bounds that we obtain with this analysis are reliable security guarantees with respect to the underlying formal model of execution. When we apply this program analysis step to OpenSSL AES in the lookup table-based version, we get non-zero leakage bounds across all attacker models. It's not really surprising that this is a non-zero bound because there are these known attacks against lookup table-based AES implementations, so it was kind of expected that this will be non-zero. But this means that some mitigation has to happen, and in this case, then the second stage of RiCaSi, the circuit compilation, is invoked.
The circuit compilation step of RiCaSi compiles the given C code into a circuit representation, which in turn is compiled into an x86 binary for further analysis. For this, we mainly rely on the state-of-the-art circuit compiler RiCaSi, published by Bücher et al. At CCS in 2018. RiCaSi was originally designed to produce optimized circuits for mixed protocol MPC frameworks from ANSI C, but for our purposes we only rely on its capability to produce size-optimized Boolean circuits in the widely known Bristol circuit format, so we can skip most of the computationally expensive steps like decomposing the code into separate modules and compiling each module into multiple different types of circuits. Since RiCaSi currently comes with some limitations regarding the processable source code, we first have to do some semi-automatic pre-processing, where we, for example, have to eliminate global and static variables and replace pointers that are used as function arguments. After that, RiCaSi automatically transforms the code into a go-to intermediate representation. Loops are unrolled, variables are split into single bits, operations over those bits are expressed as Boolean functions, which are then optimized for circuit minimization. The resulting human-readable Bristol format output for our OpenSSL AES example then looks something like this. For transforming this circuit representation back to C code that can be compiled into an x86 binary, we implemented our own tool in Python. This tool basically iterates through the topologically ordered circuit description and inserts the respective C instruction for performing the specified gate operation and declares variables to be used instead of wires. The resulting source code can then be compiled into an x86 binary and is ready for further analysis.
In the final step of RiCaSi, then the second round of program analysis is applied to the binary. The analysis is the same one that has been used already in the first phase of RiCaSi, but this time it is applied to the x86 binary of the implementation with the mitigation. In the case of OpenSSL AES, this implementation looks roughly like this. So we have wires, quite a lot of them actually, and between these wires we have XOR operations, we have negations, we have AND operations, which mimic the logic gates. And when we then analyze this resulting implementation with the program analysis, we get finally zero leakage bounds across all attacker models. So the circuit-based binary is sufficiently secure, even with respect to our strict security threshold, and we can use this hardened binary instead of the vulnerable one. Now we showed you one example for OpenSSL AES, but how does this actually compare across different implementations? We evaluated RiCaSi actually across multiple implementations, first across different AES implementations, from OpenSSL, EmbedTLS, Mantel, and libtomcrypt. You can see here they are all based on lookup tables and they all have non-zero leakage bounds for the original implementation. But in the second round of RiCaSi, actually we were able to achieve zero leakage guarantees across all attacker models for all 4 AES implementations. We also applied RiCaSi to other crypto implementations beyond AES, namely to Camellia, DES, and Triple DES from EmbedTLS. Again, the original implementations had all non-zero leakage bounds, and after the application of the second phase of RiCaSi, we get zero leakage guarantees for all of these implementations. That is, the RiCaSi toolchain is effective across the different AES implementations and across the different crypto implementations in our evaluation.
We evaluated the overhead of RiCaSi in case the code had to undergo circuit compilation in 2 dimensions, namely the size of circuit-based binaries and the runtime of the side channel resistant binaries compared to the vulnerable counterparts. For the binary size, we can see that the overhead of circuit compilation is about 2 orders of magnitude for our AES example. So while a binary with a size of around 24 megabytes is still manageable, we of course recommend to use RiCaSi mainly on small, highly security critical code sections. Likewise, for the corresponding runtime, evaluated on 1 core of an Intel Core i9 CPU, we observed 2 orders of magnitude overhead for our DES and triple DES examples, and 3 orders of magnitude for Camellia and all AES implementations here on the right-hand side. For encrypting large amounts of data or applications with strict real-time requirements, this overhead obviously becomes impractical. However, for processing small or even large amounts of data in high security contexts without strict real-time requirements, the circuit-based binaries generated by RiCaSi can deliver practical performance.
So overall, we have shown you our approach that combines circuit compilation and program analysis for cache side channel mitigation. Our RiCaSi toolchain was very effective in our evaluation, and we think that the combination of circuit compilation and program analysis looks like a promising direction for cache side channel mitigation. There are multiple directions for optimizing the approach further in the future. For example, optimizing the circuits to obtain smaller binaries and optimizing the circuits to obtain faster binaries. For example, it will be an interesting direction to consider bit slicing of circuits to increase the performance. It will also be interesting to see how RiCaSi can be improved by implementing ORAM, so oblivious RAM, for selected parts of the code, for example to replace lookup tables. And it would also be interesting to expand the scope of RiCaSi to other use cases beyond crypto implementations. To sum up, we have presented our idea for cache-side channel mitigation, which allows developers to work on the high level of abstraction that they are used to, but still provides them with circuit-based executables that come also with security guarantees, and that only selectively introduces overhead where necessary to obtain these security guarantees. We have shown you the implementation of this approach in the toolchain RiCaSi, and the evaluation on different vulnerable crypto implementations which we successfully managed to secure with RiCaSi. If you're interested to find out more about RiCaSi, the article with the full walkthrough through RiCaSi with all details on the evaluation will appear in the proceedings of CANS 2020, and there are also supplementary downloads which are available on our website for code and for case studies. With this, I would like to conclude and thank you for your attention.